Hello there, welcome back to the Professor's Du Bois channel. This is Professor Victoria and Professor Corey, and today we are continuing with our buffer series. This is part 2, so if you need help with what a buffer is and how it works, you might want to go back to part 1. We're going to be starting some calculations today, and today we're going to be working on calculating the pH of a buffer solution given a concentration of both your conjugate acid and your conjugate base. Now keep in mind that you may need to calculate these concentrations if you were provided, say, some amount of moles or amount of grams of these. You might have to calculate these concentrations. But once you have the concentrations, we're going to talk about how to calculate the pH of that buffer solution.
Yeah, so going back, we talked about this in our first video in the series. We like to write the acid hydrolysis, and sometimes it's a little tricky trying to figure out what your acid is. Now, there's a couple of clues here. One clue is they gave us the Ka, and they put it right near the acid, and oftentimes you'll see that. So sometimes you can identify it just based on that, but you can always fall back on just counting the number of hydrogens. So your acid is going to have one more hydrogen than your base. And once you've identified which is your acid, we strongly recommend writing an acid hydrolysis reaction.
What that does too is it forces you to have your conjugate acid-base pairs on opposite sides of the arrow. And a lot of times people will think, okay, well, I'm adding this conjugate acid and base together, which is what you do, in the lab. You would put both of them together, but they wouldn't be both reactants as if you were putting them together and they were reacting together. That's not true. They are on opposite sides of this equilibrium.
Yeah, and by writing the acid hydrolysis, we have our hydronium ion in our equation, which makes finding the pH pretty easy. So we're going to do this using an ice table, and then we're going to show you a different method that we actually prefer. Mm-hmm. So we can say initially, we can just put in these values. We've got the 0.311 molar. I can stay in molarity here. For our base, and
in fact you'd want to stay in molarity for an ice table.
0.362, and we would say we have none of this to begin with, so our change is going to have to go up on the right. We don't know how much, so we're just going to represent that with x. Now here we could also put plus x, and we could write minus x over here. But we have a Ka value here that is so small. It's so small that really at our equilibrium, the change, the x, is going to be very, very small compared to 0.3. Now, it is going to be significant compared to 0. So at equilibrium, we will have x for our H3O plus concentration. But we can safely say that we're going to be about 0.311 in our base and about 0.362 in our acid. Now, the method we use, we take the Ka value and multiply it by 100 and compare it to those initial concentrations. If that is smaller, the Ka times 100 is smaller than the initial concentration, it is safe to use this assumption method that the change, the x value, is going to be small relative to that amount. So we have our K value in our K expression, right? This would be the equilibrium concentration. I'm put brackets for my concentration of my base times the hydronium ion.
So you're doing products over reactants?
Over my acid.
Now we would raise these to the power of their coefficients, but in this case everything's a 1-to-1 ratio, and that's why we also have just the single x's. We don't have any 2x's or 3x's because everything's in a 1-to-1 ratio. So there's our K value, and our products over reactants, we've got 0.311 times x divided by our 0.362, and this is our K for this hydrolysis reaction.
So I'm going to assume that you can do this algebra, and so essentially what we're going to do is solve for x. I did this by multiplying both sides by 0.362, and then dividing both sides by 0.311, and I've got a value for x.
2.77 times 10 to the minus 11th. Now that's your hydronium ion concentration because we solve for x, and our x represents our hydronium in that final row of our ice table. So to get the pH then, the pH is just simply the negative log of our hydronium ion concentration. So in your calculator, you will want to do the log of 2.77 times 10 to the minus 11th, and then take the negative of that, and your pH ends up being 10.557. And we have 3 decimal places because we have 3 significant figures in our concentration, and that came from 3 significant figures of our Ka and our concentrations.
All right.
So there you have it.
So now let's show you another method for solving the same problem. We can use what's called the Henderson-Hasselbalch equation. And let me put this in a different color.
Okay.
And this equation looks something like this. We can say the pH is equal to the pKa. You want to talk about the pKa?
Yeah, pKa. P is just a it's just a mathematical function. So just like taking the P of the H to get our pH of our hydronium ion concentration, we can take the negative log of our Ka to get our pKa. And this just puts the numbers into some manageable whole numbers, things that we like to work with a little bit more than times 10 to the minus 11th. So our pKa of our Ka is 10.623.
How'd you get that again?
Again, I took the 2.38 times 10 to the minus 11th. That's the Ka. Took the log of it and then multiplied by minus 1. So took the negative of it. So there's your pKa, and your pH of your buffer solution will be quite close to your pKa.
So the way I'm going to solve this, I'm going to take my 0.311 and divide by 0.362 and then just hit log on my calculator. And I'm going to add that value to the 10.623. And sure enough, I get 10.557, just like I did using my ice table.
Either one can work, either one's fine, as long as you have an amount, a significant amount of both your acid and your conjugate base. You can use this Henderson-Hasselbalch. You would not want to do this just for a simple hydrolysis of a single entity, just your acid, for example. If you put your acid in water and let it come to equilibrium, you would want to generate that ice table and use the Ka for that rather than the Henderson-Hasselbalch. Use your Henderson-Hasselbalch when you have a buffer, when you have some of your acid and your conjugate base, or some of your weak base and some of your conjugate acid. And it works. Very good. We have one for you.
Yeah, so why don't you pause this video and give this problem a try on your own. So just pause the video, see if you can work through it. It's very similar, and when you restart the video, we'll do a quick walk through it using the Hasselbalch equation, because we do have a buffer solution here. Mm-hmm. We'll use the Hasselbalch equation and we can compare results.
So here's your Henderson-Hasselbalch equation. pKa equals, or pH equals the pKa plus the log, and we say just base over acid. So this is your concentration of base over your concentration of acid, or you can have your moles of base over your moles of acid. In a future video in this series, we'll talk about that more.
All right, so we have a Ka value, and that kind of helped me identify, notice how that was with the acid. But I'm just going to check to make sure and compare my two conjugates, and this one does have one more hydrogen. So the H2PO4 is the acid that goes in the denominator here. So I can say my pH is equal to my pKa. I have the Ka, so I have to take the negative log of this Ka value. And the way I do that is I enter this value and hit log, and then make that value negative. So I got 7.21. Now why is 7.21? We had 2 sig figs in that Ka value. So the 2 sig figs, that's going to correspond to 2 decimal places in the pH. And this is going to be plus the log of 0.260, that's my base, over 0.391. That's my acid. And so I'm going to do the division and take the log, add it to 7.21, and I get 7.03. Now, you may want to try this with an ice table. If you're more comfortable with the ice table, you can just use the ice table. We prefer the Hasselbalch equation. It just seems like it's quicker or it's easier. I'm not sure.
I kind of like it.
Yeah, I definitely prefer the Hasselbalch equation.
All right, so this wraps up this video. Please join us for more videos in our buffer series. We're going to get into a little bit more complicated buffer questions, and we'll make you sharp with buffers for sure. We've got a lot in store. So come on back. Bye-bye.